Let f be a vector field and let C be a smooth curve with parameterization RT, equaling xt comma yt, where t is between a and b. Let nt equal y prime t comma negative x prime t. The flux of f across C is f dot nds, the integral, and that equals the integral of FRT, and that simply means I plug in RT into my vector field F for any x, y, or z if we had it. And then my NT, which is y prime t comma negative x prime t, and we're going to dot those and we're going to do that integral. And this is calculating flux across a curve. Now let's take a look at 91 below here. It says let f equal, and this is a vector field, x squared plus y cubed I plus 2xyj. It says calculate flux f oriented counterclockwise across the curve x squared plus y squared equals 9. So hopefully you realize from this curve here that x squared plus y squared is actually a circle of radius 3, because x squared plus y squared equals r squared. So r is going to represent not 9, but 3 because it's being squared. So let's take a look at that graph of that curve. So there's our curve. So one other thing to consider is we also have an orientation counterclockwise across this curve C. So we're going to have to think about the orientation as well. So the first thing I think of when I think of any circle is I think of x equals r cos theta and y equals r sine theta. And those are polar coordinates. And we realize that this is going to give us a circle. Now our r here is in 3. I was going to say 9, but it's 3. And that means here that our radius should be 3. So the way that's going to look is our RT is going to equal 3 cos t, comma 3 sine t. Now again, I'm going to have to work with this a little because the orientation could be in the wrong direction. Because remember, we're supposed to go counterclockwise. So what I'm going to do is I'm just going to pick a few t, starting at t equals 0. And for my first component, if I plug in 0 for cosine there, it's going to be 1. 1 times 3 is 3. So for the first ordered pair, the first component, I get a 3. For the second component, when I plug in 0 for t, sine of 0 is 0 times 3 is 0. So it's going to give me the point 30. So now let's look at t equals pi halves. Now again, I'm picking these values because for cosine and sine, those are the nice values. So pi halves here, I'm going to plug that in for t. And that's going to give me 0 there. So 3 times 0 is 0, so I get a 0 here. And for the second component here, I plug in a pi halves for that, t there, and that's going to be 1 times 3, which is 3. Now that's enough to see what's going on here. So again, my first point is 3, 0. And my next point is 0, 3, which is here. And that tells me that I'm going in that direction. So that orientation is counterclockwise. So that's nice to check. And we definitely have to check that, or our integral could give us a wrong sign, like it could be positive instead of a negative. When we look at the graph, that could be confusing. So we got to make sure we're going in the right direction with these curves as well. So then the orientation, like I said, is going in this direction. Okay, so now let's talk about F. Because if you look at our formula here, and again, that's all I'm trying to do here, is I'm trying to set up all the components for our integral so that we can integrate. So far, we didn't really find anything yet, but we did find the RT that we're supposed to plug into F. So let's do that now. So here's our F. So for X, I'm going to plug in 3 cosine t. For Y, I'm going to plug in 3 sine t. So for the first one, it's x squared. So I'm just going to do this outright. This is going to be 9 cosine squared t. When I plug it in, that's what I'm going to get. I have a plus here, and then I'm going to do a 9, and then it's going to be y cubed. I have to plug in 3 sine of t for y. Oh, so that's not going to be 9. Sorry about that. That's going to be 27 because it's cubed. And that's going to be sine cubed t. And that's going to be my f. Oh, my first part of my f. Now for the second part, it's going to be 2. And I'm going to write that out so that we can keep track of it all. So that's going to be 3 cosine t. And then for my y here, now I'm right there, that's going to be 3 sine of t. So there it is. And then I'm going to clean it up a little more here, definitely. I did the first half already. Cosine squared t plus 27 sine cubed t, comma. And this is going to end up being 18 cosine t sine t. So there it is. So that's my f here. So we're going to get rid of this one above it just for the sake of room here. Got to make sure we try to keep a clean slate as much as we can. Going to move that up here. Okay, now we need one more piece. We need nt. So here's our n. So the first component for the n is supposed to be y prime t. So that's our second component of our RT here, and then I have to take the derivative of that, so that's going to be 3 cosine t. Now we're going to look at the second piece here for our n, and that's going to be negative x prime t. So we take the first component of RT, which is 3 cos t, we take that derivative, and it tells us to negate it, so I'm going to put a negative there, and that's going to be negative 3 did it again. Negative 3 sine t. There it is. And that's our second one. So our n then, when simplified, not much to simplify here, but definitely a little bit of simplification. This is going to be 3 sine of t. So there's our nt. Now we have all of the information to put this thing together and work it out as far as that integral is concerned and find the flux of f across C. All right, so I'm just going to take this now and just move it upward, just so we have everything kind of condensed here, because we're going to need as much room as we can. Now we don't need this anymore either. We're done with that. Now let's set up that integral. So we have the integral. Let's talk about bounds. All right, so I'll have to go back a step. All right, so for the bounds of this, we're starting here and we're going all the way around. So if we're going all the way around the circle that way, our bounds are going to be from 0 to 2 pi. All right, now we can get rid of it. So now we have the integral from 0 to 2 pi, and our FRT there is going to be 9 cosine squared t plus 27 sine cubed t. One thing I realized, I'm writing it out first, okay. I thought I was doing a dot product already, but I'm not. Okay, so I'm okay. So 18 cosine t, sine t, and there's the first one, dotted with 3 cosine t, comma, 3 sine t. So there we go, dt. Okay, so now what we're going to do is we're going to actually take that dot product and simplify it the best we can. So when I multiply this first component by that first component there, I'm going to get 27 cosine cubed t plus 81 sine squared t cosine t, and then now I'm going to take this second one and multiply it through. So plus 18 times 3, which is 54 cosine t sine squared t, and that would be dt. So I had one mistake in here I noticed. I just caught it when I was getting ready to multiply. That should be a cubed there. All right, and everything else is okay because that was that sine cube there that I multiplied by cosine. All right, so that's the only thing I screwed up on that. So now we can actually integrate this, and we get 81/4 sine of 4th t plus 9 sine cube t plus 27 sine of t. And then that's going to be from 0 to 2 pi, which when I plug in all those upper bounds, the sine of 2 pi is 0, and that'll be for each of these. And the sine of 2 pi is 0, so those are all going to be 0, minus the lower bound when I plug in all of these t's here. The sine of 0, even though I'm taking it to the 4th, is still going to be 0 for each of those. So this integral ends up being 0. Now again, these problems wouldn't be hard to do by u substitution. I just didn't go through it with these problems, but that's something you can do on your own. If you feel comfortable with it, that's great. If you don't, get a hold of me. So that's the answer here for this. So what this is saying here is that the flux of F across C is 0. So, and we think about that circle here. When we had this circle, it's saying that, remember, it's outward flux. So is the vectors pointing outwards from the curve or inwards from the curve? And what it's saying is, all together, when I go all around it, it's 0. So either all the vectors are doing nothing for me, or they're canceling each other out by maybe a portion going inward and another portion going outward. So it could be something like this going on, possibly. And we wouldn't know unless we graph the vector field and the curve on that to see what the vectors are doing. All right, but there we go.